Session, I'm going to continue the last concept what we discussed, that is least square method using linear regression. So we have discussed in the last class what is this dependent variable, independent variable, and applications of linear regression. In the same way, I have discussed one the slope line equation, that is y equal to mx plus c, that is regression equation, and this a simple example today we'll discuss the continuation of the last class, that is coefficient calculation with the least square method. And what is this intuition behind the regression line? Let's consider a sample data set with 5 rows and we'll find out how to draw the regression line. So this is the independent variable x and this is the dependent variable y. And let us plot these data points onto a graph. See, this is dependent and this is independent variable. For 1, the y variable is 2. So that's why we are plotting here. And for 2, it is 4. We have plotted here. And for 3, it is 5. 4, it is 4. 5, it is 5. So in this way, we are going to plot the data points. And this we are going to predict using the regression line. Now, the next one. First, the very first thing is we have to find out the mean of x variable and mean of the y variable. And this regression line, whenever we are drawing a regression line, it should ideally pass through the mean of x and y. So after calculating this x and y, we got mean values as 3 and 4, that is 3 and 4. So here we are plotting this mean value, that is 3, 4. So you have to draw a line in such a way that it should pass through this mean of x and y. So this is how we have drawn this line. Now, we know that slope line equation of this regression line, that is y equal to mx plus c. Now, we know the y values, we know the x values, but we have to find out this m value and c value. So, this linear equation they represented by this mx plus c. So, how we are going to find out the m value, slope value? That is, there is a formula, that is n into sigma x into y minus sigma x into sigma y divided by n into sigma x square minus sigma x whole square. So substitute all these values x, y, x square, x whole square into this. At last we got the answer as m equal to 0.6. Similarly, coming to the coefficient c, again we have a formula, that is sigma y into sigma x square minus sigma x into sigma x into y divided by n into sigma x square into sigma x whole square. Again, substitute all these x, y, x square, x whole square, x into y values into this. After calculation, we'll get c value as 2.2. Now we know m value, we know c value, and already we know y and x values. So place all these values for each and every value. See, y means actual values already we have given. Now we are predicting. Now y equal to 0.6 into 1 plus 2. The very first x value is 2. We got 2.8. Next, when x is equal to again 2, we got 3, 4. Next, we got 4. That is 3 value. Next, 4, we got 4.6, and next x value is 5, we got 5.2. So these are the predicted values. We have actual values. Now we got the predicted values. Now here let us place these data points. Here the blue point, here already we have plotted these blue points, that is these are the actual y values, and these brown points represent the predicted y values. Okay, now what we have calculated these values, those are predicted value, and we have represented it with brown points. So the distance between the actual and predicted values are known as residuals or errors. In the last class, last session, we discussed this, what is this residual or error. So actual minus predicted values are known as the residuals, or simply we call it as the errors. So the best fit line should have the least sum of squares of these errors and the least square. So when we calculate these actual minus predicted, we should get least sum of squares of these errors. Then we can say that it is the best fit line. Now, see, one more table we have drawn here. So we know x value, y value. This is the predicted value. Now, uh, find out y minus y predicted. That is actual minus predicted. We got this one and square this one, and sum of these square is equal to 2.4. So for this particular equation, for this particular data set, the sum of squared errors for the regression line is 2.4. So now we are going to check this error for each line, and we are going to conclude the best fit line having the least e square error. Now, after finding out this, okay, just what we have to do is we have to minimize the distance. So how we are going to minimize the distances? There are lots of ways to minimize this distance. Okay. So sum of squared errors or sum of absolute errors are root mean square. So what we are going to do is we keep on moving this line through the data points to make sure that the best line has the least square distance between the data points and the regression line. This we are keep on moving this regression line like this, just with some distance like this. We are going to draw different regression lines, and at last we are going to calculate these errors, sum of square errors, for which line it is showing the least sum of square errors. That we are going to take it as the regression line which best fits our data. This is how we are going to find out the best fit line. And we are going to square all these things which we are having the least, that we are going to take it as a best fit line. So this is how we are going to find out the coefficient using the least square method. And coming to this types of linear regression, till now what we discussed is it is simple linear regression, which is represented by y equal to mx plus c. Then coming to this next one is multiple linear regression. Here, what is this simple linear regression? Here we'll have only one independent variable and one dependent variable. But whereas coming to the multiple linear regression, we'll have more than one independent variables. Okay. And single dependent variable. That is what the difference between simple linear regression and multiple linear regression. And this is the equation. You can see m1 into x1 plus m2 into x2, so and m1 into xn plus c, where these m1, m2 are the slopes. This is coefficient, and we already know this is dependent variable, and this is the independent variable. X is the. Okay. Now, we have to implement this linear regression. Even in lab, when we discuss this lab, week 4 belongs to this implementation of linear regression. Now we will see how we are going to implement this linear regression. So the very first thing for any machine learning program is we have to import the libraries. In that, there are main three libraries are there. One is NumPy, one is Pandas, and one is the Matplotlib. First, import the libraries. Importing the libraries is the first step in implementing the linear regression program. Okay. So Seaborn is used for data visualization. And then the second step is we have to load the data set. We have already acquired the data set. We have collected the data set either from Kaggle or UCAML repository. And now we have to import the data set into our program. For that, we are going to use a method called as pdread_csv, the URL of the particular data set. And then we have to extract the independent variables and dependent variables. Why? Because our main agenda regarding linear regression is we need one independent variable and one dependent variable. For that, we need to extract this independent and dependent variable. For that, we are going to use a function called as ilog. Okay, index location -1 indicates before, except this one, remaining all we are extracting, and this is the fourth column indicates the dependent variable. Okay. Now, this head indicates the first 5 rows of the given data set. So, this is the first 5 rows of the data set. And the next step is data visualization. Okay, this we are seeing with the help of a heat map, we are going to find out the correlation between all the variables. For that, we use this SNS, that is Seaborn, for data visualization. And the next one, this is the same one. And next one is encoding the categorical data. In the data pre-processing step only, I told you, we have to encode the categorical data. What do you mean by this categorical data? See here, this is the data set. When you see this data set, observe this state column. We have string data, where a machine learning algorithm can't understand the string data, we have to convert it into vectors, which is understandable by our ML model. For that, we are going to encode this categorical data. That is, for this encoding categorical data, from sklearn.preprocessing, we are going to import two methods called as label encoder and one hot encoder, where we are going to convert this particular categorical data into vectors. Okay? So we are going to create a method label encoder and we are going to fit that data, and one with the help of one hot encoder, we are going to this third column which we have state column, that we are going to convert it into an array. We are going to fit into this one hot encoder and transforming that into array. So this encoding categorical data is not required for each and every data set. Whenever we find categorical data in a data set, then only you have to perform this encoding categorical data. So now, once after doing this, now the state column, what we have seen, that is converted into vectors. Now, the very next step is a very important step, that is the splitting the data set into training and testing. Okay. So here you can see that 20% of the data we have taken in for testing, and remaining 80% we have given for training. And we are implementing linear regression. So from sklearn.linear_model, we have to import linear regression, and we are going to fit this linear regression model for training the X-trained data and the Y-trained data. Now, the very important step in this linear regression is we have to find out the regression and the intercept. That is, we have to find out the M value and the C value. For that, we are going to use a method called as regressor. Okay, here we are predicting the X data. Okay, we have already trained and we are predicting the test results. After that, we have to find out the coefficient and the intercept, which I already told you, that is C, and this is M. Or else we can also say B0 to B1, which we have calculated in the theory point of view. So here, this calculating the coefficients and calculating the intercept, we have a method called as regressor dot coefficient underscore and regressor dot intercept underscore. So we will find this coefficient values and intercept values. Now we have to evaluate the model. So coming to the linear regression, here the concept is not about finding the accuracy. We are going to find out the R square value. Okay. Why? Because accuracy, we are not calculating here any true positives or true negatives. Just we have to find out how much this square value will be. So here, when we test, the square value is tested against test data and the predicted data. We have tested some data and we have predicted some results. And in between, if you got a good result, so this here, the R squared value is giving you 0.91. So it proves that the model is a good model. Okay, if you get least value, now we can't say that it is the best fit line and our model is not working good. Okay, so this is how we are going to evaluate the linear regression model. And along with this, we can also evaluate three more errors, that is mean absolute error, mean square error, and root mean square error. We are going to calculate these three, and how much least errors we will get now, then we can say that our model is the best fit model. So along with this R square, we can also find out these three errors. And in the coming sessions, I'll discuss how we are going to calculate all these errors. Thank you.